For centuries, the pace of scientific discovery has been bottlenecked by a single constraint: the biological speed of human thought. A researcher can only read so many papers, run so many physical experiments, and manually iterate on so many hypotheses in a lifetime. We are moving toward automated science, where the speed of progress is no longer limited by human bandwidth, but strictly by the amount of compute power we can supply to the problem. To understand this transition, we have to look past the standard way we interact with AI today. If you type a prompt into a typical interface, you get a single-shot prediction of the next word. Automated science relies on an entirely different mechanism: agentic workflows. In an agentic workflow, a complex scientific inquiry isn't answered in one breath. The system takes a high-level goal and fractures it into a sequence of autonomous, executable subtasks. The AI stops acting as a passive tool and operates as an autonomous researcher, capable of running the entire scientific method at the speed of silicon. The architecture making this possible is what researcher Andrej Karpathy refers to as the LLM OS. In this framework, the large language model functions directly as the central processing kernel of an operating system, rather than a chatbot. This central kernel actively manages its own memory and has the authority to write and autonomously execute code within secure, isolated sandboxes. To solve problems, the kernel relies on reasoning traces. These are step-by-step logical outputs, essentially an explicit chain of thought, that allow the AI to plan and orchestrate a swarm of specialized external peripherals, such as internet search engines and mathematical solvers. This configuration shifts the LLM from a word calculator into a dynamic logic engine, equipped to dismantle complex structural problems piece by piece. This is the intelligence loop, a cyclic, four-step algorithmic process of execution and self-correction. It begins when the system breaks down a task to generate a hypothesis. From there, the agent writes the corresponding code and moves into a sandbox to physically execute it. When the code fails, the agent reads and analyzes the resulting error logs, autonomously rewrites the code to patch the bugs, and runs the cycle again. We can see this loop operating at the bedrock level in Karpathy's LLM.C project. The goal is to train GPT models using pure C and CUDA code. CUDA is a programming platform that allows software to send instructions directly to NVIDIA graphics processing units. When training speed hits a wall, Karpathy tasks the AI agent with analyzing the raw CUDA kernels. These kernels are the core computational functions executed directly on the GPU hardware. The agent scans them to identify specific inefficiencies in how memory is being accessed. The AI then outputs a technical solution, suggesting rewrites involving complex pointer arithmetic, the direct manipulation of physical memory addresses in the code, and GPU memory tiling, a technique that breaks large datasets into smaller blocks to fit inside the GPU's fast internal cache. Because the AI identifies its own bottlenecks and writes the code to fix them, it creates a closed-loop hardware-software co-design. The machine is rebuilding its own compute infrastructure. This loop is already scaling outward to dictate results in the physical sciences. This graph visualizes the output of DeepMind's GNoME project, which successfully predicted the structural stability of 2.2 million distinct, previously unknown crystal structures. To grasp the volume of that dataset, those predictions represent approximately 800 years of human experimental knowledge, generated within a single project. Proving these predictions requires synthesis. DeepMind transferred these structures to A-Lab, an autonomous robotic facility in Berkeley. Inside A-Lab, autonomous robotic arms physically mix, heat, and synthesize these new chemical compounds completely without any human intervention. Following the AI's digital predictions, the automated lab successfully synthesized 41 novel chemical compounds in just 17 days. The intelligence loop successfully dictates physical chemistry, operating at a scale that human lab workers cannot match. This loop is now being applied to the final step of the scientific method, peer-reviewed academic publishing. This is the goal of Sakana AI's The AI Scientist. The system autonomously searches literature, generates a novel research idea, and writes the experimental code. During execution, the agent runs those experiments in an isolated environment and renders its own data visualization charts based on the results. The system then outputs a standard LaTeX document. LaTeX is a typesetting software used in academia for formatting complex scientific papers. The agent compiles all text and citations, tracing its conclusions backwards to the raw Python code. To ensure accuracy, the system employs an automated peer review agent to evaluate the initial draft. This secondary agent critiques the methodology, forcing the primary scientist agent to correct its errors and rewrite the text until the work is approved for publication. Sakana AI has effectively automated the generation, validation, and documentation of scientific knowledge, removing the need for human oversight of the process. The technical driver of this acceleration is a concept known as recursive self-improvement. The process begins by tasking an advanced AI agent with one goal: optimize your own underlying neural architecture to achieve faster reasoning. As this diagram shows, an initial algorithm, AIN, writes a more efficient token processing script or a superior loss function. A loss function is a mathematical formula that measures how far an AI's predictions deviate from the correct answer, guiding how it learns. The subsequent iteration, AI to the n+1, is born from that optimized algorithm. It possesses higher efficiency and reasoning intelligence than its predecessor. AI to the n+1 then applies its upgraded capabilities to find deeper structural optimizations inside its own transformer blocks. Transformer blocks are the neural network layers that allow an AI to weigh context and relationships between data points. While human researchers rely on slow academic training to improve their output, an AI in this loop executes millions of iterative self-improvements per day. When these cycles run millions of times per day, the rate of algorithmic progress shifts from a steady incline to a vertical spike. At this speed, discovery outpaces the capacity of human researchers to monitor, verify, or even comprehend the output as it happens. In a landscape dominated by fully automated scientific discovery, the human engineer's role must change. The human role is migrating away from manual task execution and toward strategic objective setting. Researchers will no longer spend their time determining how to conduct an experiment. Their focus will be strictly defining what needs to be achieved. A scientist will prompt a swarm of AI agents with a highly constrained directive, such as locate a room temperature superconductor and ensure it can be manufactured for under $10 per kilogram. As shown in this hierarchy, the human scientist sits at the apex, architecting the mathematical fitness functions, reward mechanisms, and ethical boundaries. A fitness function is an objective scoring metric that tells the AI exactly how close a proposed solution is to the goal. Once these boundaries are set, the AI swarms are unleashed to explore the vast latent space, the mathematical representation of all possible solutions, to find the exact configuration that satisfies the constraints. With the intelligence loop closed, the primary constraint on science moves from the bandwidth of the human mind to the availability of compute, allowing for a rate of discovery limited only by the hardware we can build.